Um, we are today going to move on with chapter 5. I will repeat a little bit of Runge Kutta because this is really important for you guys for the programming assignment. So last lecture, we discussed everything you need basically for doing program assignment 3. Today we'll talk about new things, but let me start by repeating these things. Has anyone started on this yet? Any questions of general interest on the programming assignment? Yes?
So the data in part 1, are they a function of t?
Yes, what you mean the functions, the right-hand side?
Yeah, so like are y's, are the functions of theta, that's omegas, which are functions of t?
Yes. Everything is a function of t, right? So you have thetas, and they are functions of t. And omegas will also be functions of t, yeah. Your right-hand side will not be a function of t, though. If you look at your by right-hand side, I mean whatever the f, right? There will be no, in fact, you can see that I'm changing something which might confuse you guys a little bit. Namely, I'm not calling it, we always call it f of t comma y, right? Well, I'm just calling it f of y. Just pointing out that there is no explicit t dependency. Of course, y will be functions of t. But imagine a pendulum that is moving around. There's no direct dependency of t. All the forces, all the Newton's law that this comes from, they are just depending on the position y. So this might confuse you, actually. In fact, if you try to run my RK4 function, which I'll discuss more again on this, of course you need to tell it that f has a parameter t. Otherwise it breaks. Or you write it on your own, rewrite it. But yeah, this is, so part 1 here is, I guess, easy to get confused by all the expressions, but it's really as easy as those simple exercises I did last time where I rewrote a second order into a first order. We don't know how to handle two derivatives. So you turn it into a new variable, you introduce a new variable, omega 1. And then, of course, this is just one derivative of omega 1. Okay? But now you have 4 variables, which means that you need 2 more equations. But those 2 equations are here. That's really all you do in that exercise. Or for that matter, in the corresponding exercises in 5.9 on how to do this. Anyway, when you come here, you're using the Runge Kutta, and we can look at that. Anyone has been able to solve it yet? Any pendulums moving around yet? Do they look physically realistic? It's funny, you can mess up a minus sign or something here and there in those expressions, and it will start off looking good. I think if you're running a long time, you can get an impression whether it seems to gain energy or something like that. I think if you run it long enough, most of you will be able to tell if it's good. So that's a good thing about plotting it. Let me just tell you, quickly review the theory behind those Runge Kuttas. We like these high-order Taylor methods. And by the way, this is also on your homework for next week of running some of these. We basically said that Euler's method does this, where the t is just f. Assuming f is a slope, you just take a straight line. That's what Euler does. And then Taylor method say, hey, that's really like doing a Taylor and only keeping the first slope here. Why don't we just keep on going? So throwing in one more term, there's a higher derivative of the slope f, and there's an h half. That gives you a much more accurate method. The issue with this method, we did examples. The issue is computing the f prime. First of all, it was messy because this is a function of 2 variables. Both depend on time. So we had to use the multivariate, the total derivative of the multivariate function. There was also a chain rule. In fact, we did rewrite f prime as the partial derivative of f with respect to t times the inner derivative, but that's trivial. So that's 1, so we leave that. Plus the partial derivative of f with respect to u times du dt, right? The inner derivative of this guy. Sorry, y. Okay? And then we observe that, wow, but that is really f. So this is really df dt plus df dy f. Right? So you can keep on playing that game if you want higher order Taylor method. So it's doable. But then and we did it, and it's really a good method. But we realized that having to differentiate your f might be unusually much work, and maybe you don't have f accessible in an explicit form. So you don't want to do that. So the whole goal of the Runge Kuttas was to try to do this without derivatives. And to do that, first we remind ourselves of the Taylor in 2 variables. The reason there are 2 variables is that there are 2 variables here. In fact, I think almost maybe if this is confusing, it would have been more pedagogical to just forget about the t for now. Because all these equations, the t part, if you think about an order, the problems we're solving, y prime equals f, the difficult part is really the y dependency. And in fact, in the graduate course, when we teach this, we show in the beginning that you can magically just take away this t if you want to. And if you can handle the case where you have y there, you can handle anything. So don't worry too much about these two variables. But I guess it's kind of back to basics to just say this is a function of two variables, t and y, and you need Taylor. And we're just going to use the very first term here, the first row, that says that you can put a plane. You just have two partial derivatives, and there's a delta t and a delta y. And this is how we're going to use it. We like Taylor's method of order 2, where we need to compute this. In fact, this is what we call T2, which is that f plus this f prime times h half. We like it, we just don't want to compute f prime. And we're saying, but we can compute f at many points. Remember, Euler only computes f at where you're standing right now. Euler's method takes a step. Euler's method is standing here, and it computes ti, and here you have we call it wi. And it will just compute the slope, which is f of ti comma wi, okay? And that's, of course, the simplest thing you can do. But you are allowed, I'm saying I don't want to evaluate derivatives of f, but I don't mind moving around and evaluate f somewhere else. And that's what Runge Kutta methods are about. And it's kind of not immediately intuitive why, but here they kind of derive it by saying, let's say we just evaluate f somewhere else. Okay? We go a little step alpha 1 to the right and beta 1 up. And maybe we want to multiply everything by a1. That's really unnecessary. It's going to be 1. That a1, don't worry about that. It's just the idea that when you do this, of course, Taylor will tell you there will be all types of f derivatives popping out in this implicitly, right? So maybe there is a chance that you can make this approximately equal to this thing that we want. That's the idea. And working out the details, we actually just need the first term. So first of all, I'm doing this step on the f prime, saying that it's equal to df dt and the df dy times, well, this y prime will be replaced by f further down. So this is really the Taylor method of order 2 that you might want to write it. In fact, this expression is what you will use in practice, where you just plug this into that method. All right, so this is what we want. And we observe that there is a partial derivative of f with respect to t, 1 with respect to y multiplying f. And hopefully this will pop out so we can compensate for it. Now let's go back to this expression. Let's try to tailor this and see if it can have those terms. And it can. Very simple Taylor. This is just the first two terms, just the linear terms. The a1 just multiplies everything. So it's f of t comma y, that's what Taylor says, f. And then remember, it's plus h times the derivative. And in multi-dimension, that means plus the delta, the step in t times df dt, plus the step in y, which was b1, beta 1, times df dy. That's all. It's just really the first order two-variable Taylor polynomial. And then there's a remainder that we can discuss later. But we stop here. And what we observe is that this, by moving a little bit to the side, we got the f out, of course, but we also get perturbations involving df dt and df dy. Okay? And maybe you can choose these coefficients so that it matches this thing down here, which is also mostly f, but it's also perturbations involving df dt and df dy. Just, you can match them. And by matching and just observing here, the a1, as I said, is obviously 1. But you get this equation. But you can solve it easily and see that if you set alpha 1 to h half, then you will match the first term. And then you actually have to set beta 1 to h half times f, which is OK, because we allow ourselves to evaluate f. So plugging all this in, let's look at the error term in a little bit. But here's how you can write it, that I said that I'm going to move a little bit to the side by alpha 1, that's h half, and a little bit up by h half times f. And this is a new method. Okay? And it's, as we just said, it matches the second order Taylor method at least up to those first terms. So maybe it's a good method. And it's called the midpoint method. It's kind of funky looking. It's nested f. And by that I mean that there's an f in here, then you do stuff, and then you do f again. I did a MATLAB code of one-liner. I don't think you should do this one-liners, but it's just two calls to f. And it's so much better than having to differentiate f. You'll see when you run these examples that there's no reason to do this method. The accuracy, you can show that the things we threw away are order h squared. Is that bad? So we're not matching the Taylor method exactly. But remember, the Taylor method wasn't perfect to begin with. So if you're doing this, playing this game and approximating, and it's close enough, that's a new method. In fact, in our little test last time, I think this one looked even to be twice as good as the other one. That's kind of random. But that's not the point. The point is that we're matching the terms that we care about. Very simple method. Midpoint method of order 2. So I think the book is doing a good pedagogical job of saying, I like the step of saying, we like to do this. We don't want to differentiate. Let's see if we can just move around a little bit. But then Runge-Kutta methods get very complicated. And in fact, the one you're going to use that is very popular is this RK4, where you move around a lot. And seeing that there's no intuitive feeling. I did mention that this one you can almost see what's going on by a figure something like this, where you're standing at Ti. And Euler, this is the Euler step, right? It wants to go there, and here's the true solution, and that's not good. So what we do instead is that we just go half a step. We just go half a step up here. Okay? At that point, what do you do at that point? You evaluate a new f, a new slope. Okay? Then you take that slope and add back h times that slope to the original here. And presumably it will give you a better estimate. I mean, I'm not saying it's better by this figure because I kind of made up the slopes, but that's graphically what I'm doing. I'm taking Euler step. If you look at Wi plus h half f, that's exactly Euler with h half, right? So I'm taking half an Euler step, and then I'm evaluating a new f, and going back and doing a full Euler step with that slope. That's what the method is. I mentioned that we like to write this in a different form, where you unnest it. So instead of writing it like this, I mean, it's identical, but we like to write it by saying there's a K1, which is this f, the inner one, f of T1. Actually, let's put the h here. Sometimes people do, sometimes they don't, but the book does. You see, this is the innermost f, right? Except for the half. And then you have another f. So each time you call f, you make a k out of it. But then there will be these offsets. So here's an offset. And these offsets are in terms of k's. So you should convince yourself that these two steps are computing exactly the same f as up there, or the two f's, so to speak, so that at the end you can say Wi plus 1 equals Wi plus a full step a. It's really just k2. Right? So it's the same thing. Just convince yourself of that. Why is this nice? Computers kind of like this better. It looks better. But especially when you go up in order now, if you look at this RK4, I think I actually did assign a homework problem for next week where you're supposed to do the opposite. Take this unnested version and nest it like that. I don't remember the problem exactly, but you know, it's the same thing. But imagine here, I'm computing 4 Ks that depend on each other. So you know, there are Fs nested deep inside. But the end result is a very simple scheme. Compute an F, do a little bit of arithmetic, compute another F, and add them up. This scheme generalizes that. It computes exactly the same two, K1 and K2, as midpoint method. But then it keeps on going with steps that are very counterintuitive. I mean, I could draw a figure like this saying what it does. If you just look at the third step, the K2 is this slope here, right? The K3 takes half a step of this and evaluates a new slope here. And then a K4 goes back to the beginning and does a step of that, etc. It gets messy. And the only way to understand this is by doing the Taylor and the analysis. And you can show this is a really accurate method. And at the end, you don't even add up just K2 like here. You add up a weighted combination of all of the Ks. So it gets complicated. This method we won't analyze, but it can be shown that it's order H4. Extremely accurate method, very simple to use. I did talk about the implementation of this. And we looked at the RK4. You can use this function, but you also have to understand its limitations and the issues. You might have to edit it. In particular, I mentioned you might want to plot your pendulum, which means that you have to go in here and at least put that pendulum in there. I also mentioned that we make this f always a function of t, y, because that's what the book says we should do, and it's the general case. Now, if you write the code and you know that f doesn't depend on y, for example, my model problem that I always do is y prime equals y, right? And there are a lot of problems where there is no t here. And if you write a code from that from the beginning, Why would you include the t? And the pendulum is one of those. It's actually called an autonomous equation. If you have an equation that doesn't depend on t, if you look at this expression here, so the y here are these thetas, right? And as I said, you will, of course, rewrite it involving the omegas as well. But there will be no t's. What do you think will bring a t into that equation? What type of physics? So basically what it's saying is that if you do an experiment with this pendulum, let's say you lift it up and you let it go or something, right, which you're going to do, there's no explicit t dependence. It means that it's what we would say translation invariant in t, right? If you do it 10 seconds later, it will do exactly the same thing. There is no t in that equation. If you want to make it t-dependent, what about an external force? What if there is you're doing this. You have some engine that is pulsating it and applying an external force. That would be an external t dependency, right? Then it would not be identical if you moved it a little bit in time. So autonomous equations are very common. I know many of you will be confused by the f now is really just not a function of t comma y. So if you send that into this function, of course it will freak out because it's trying to call f with a t and a y or a w, right? So that doesn't work. So whatever you want to do, put a t there or change this function. The implementation here is really straightforward except that it's vectorized. That might confuse you. So if you kind of just look at it in general, the steps should be fairly easy. There's a big for loop taking n steps. Each step you're doing these things, but for that more advanced method. What can we see here? We can see all these offsets popping up. You see how you compute a k1, you use the k1, k2, k3, you add them up at the end. This vectorization mostly you see as a bunch of comma colon. And this is a big power of MATLAB, that it can do huge vectors at the same time. So this was that second part that you will have to use this for your pendulum. Why? Because it's really not a scalar. Everything we've done so far have been scalars, right? But now y is going to be not only the theta and the omega, but there are two thetas and two omegas. You have 4 unknowns. After problem 1, after you've done this here, you have 4 equations and 4 variables. Okay? And it's all good. And this is, as I said, unfortunately put at the end of the book. So I moved it up and talked about it already now, but my slides follow the book. So this is on the topic of higher order. First of all, they define what it means to have a system of differential equation. And I think you know that from OD Math 54, right? Yeah. That a system of differential equation is quite easy to define. It's really just saying that you have a bunch of variables, u1, u2, all the way to um. I don't know why they renamed it u now, when it was y before, it doesn't matter. And the point here is that each of these f's still depend on t comma y, or u in this case, but there are many u's. And all depend on all. If they didn't depend on each other, it would be easier, right? Then it would just be a bunch of independent scalar equations. But in general, they all depend on each other. So this is what you're going to get. And it's a very straightforward generalization. I think the point I said was, I don't have a slide on that. But the point I said about this is that instead of, I would never write it like that. You really just write it just like before and say that you have a system of ODs. And you write it in the form y prime, just like before, but now y is a vector. And you say that this is equal to some slope f, which is also a vector because there are many slopes, one for each equation. And this is now a function. Time is still scalar. Don't put a vector on the time. That's clearly indicated there as well. There's just one time. But it of course, depends on any of your variables in y. So everything we've done before, just putting appropriate vector signs, will just generalize. And that's the idea here. There's some theory here that we'll cover when we get there. But just a word about the numerical methods. The way they change is really, you can convince yourself that it's really vectorized generalizations of what we did before. So if you want to play all these things, let's say just Euler. Euler said you need a slope and you take a step. What if I have another curve up here called u2? Well, you do exactly the same thing. You compute the slope. So what you're doing is that you're computing all the slopes and adding them to all the u's. And that's the same thing as just taking your method. Let's say we do an Euler of this. You're computing all the slopes, k1. It's a vector. And you're adding it to your w times h. It's just a straightforward generalization. All of these methods generalize in the same way. So that's the good news. Solving systems is really easy. Your MATLAB code, of course, has to know that it's a vector. And that's a little tricky. So if you look at, let me show you the details of this, particularly this W here. What do you expect the shape of this W to be? If you have a system of 4 equations, for example, I mean, you want to output all of them. So T is easy. T is really just a vector with times. And in fact, I compute it immediately, and it's done, right? That's not the hard part of this function. But it should be done. So that's the first output. What times are you computing? And it's, of course, a vector starting at A, going to B in steps of H. What about W? It needs to have one number for each, but it's a vector, right? So this W here, I made into a vector, or sorry, a matrix. And in your case, it's going to be 4 variables per time step, right? So here's the time step, basically. So this would be time 0. Then comes another one at time 1, etc., right? And when everything is said and done, you get n plus 1 by 4 matrix coming out. It's actually fairly straightforward. I mean, if you only had a scalar, this would just be a vector. Oops, sorry. It would just be a vector just like T. But now for each time you have 4 variables, well, let's just make it a matrix. It's one way to make it. This is how the natural way to do it in MATLAB. This explains why I keep on doing things like W of I, colon. You should know your MATLAB now. That this means grab the entire row I. Okay? So whenever you want to talk about the vector Wi and plug into this equation, well, you just go and grab the ith vector here, and you take it out. And it's a 4 by 1 vector, 1 by 4. And you can see that that's what we're doing here. All right? A little bit of MATLAB magic, but it's kind of nice. It means you can plug all that in. I did an example, I think, last time, where we did, well, I did 2 examples. But in particular, we did the rewriting, where we said that you can get systems in many ways. Maybe your system, in this case, had 2 thetas to begin with. Then we get 2 extra ones because we had to do the trick of the second derivative. So wherever you get these numbers from. But I had, what was my example? Here's my example. This came from a damped, it was y double prime plus y prime plus 2y. Very simple math 1B problem that you could solve. The way you use it is that now y has 2 components. In your case, it will be 4. You can access them as a MATLAB vector by y of 1, y of 2, y of 2, 3, y of 4, right? You need to, f has to be a vector, so you see there's a comma, there is 2 numbers. So y is a vector, and f is a vector. T is not a vector, but I'm not using t here. And then when you've done this, you can just call the function RK4, f going from 0 to 1, what else? Alpha, initial condition, is also a vector. Maybe we should do that separately. If everything is vector valued, you need to give me one starting condition for each of the variables, right? So in this case, both the y1 and the y2 needs to start. Let's start at 1. And then you can do, then you can run it as RK4 f from 0 to 1. This is kind of cool that MATLAB gives you the hint. And then you have to tell it how many steps. Maybe that's the way to do it. And there's the solution. I think we should go a little further here. And if I went too far, it's, well, that's nice. Just looking at this, I can tell that this is, of course, plotting 2 variables now. That's also a little bit of MATLAB magic. It identifies that, what is the shape of this W? I took 100 steps. So it's 101, not numbers, because at each step there are 2 variables, right? So this is a 101 by 2 matrix. And then MATLAB is smart enough to realize, hey, maybe he wants to plot 2 curves. And it's doing it here. And I suppose the green one is the actual u or y, and the blue one is the derivative. No, the other way around. You can tell that the blue one has derivative 1 here. It doesn't matter. You'll figure it out. But they both are there. So that's kind of cool. In your case, you could plot the pendulum like this, but it will be a disaster. A better way to look at a pendulum is by an animation, as I said, using my pendplot function. Yeah, what else? That's kind of it. That should be enough for you guys to do all these, all of these problems, the various initial conditions. See how it works. Now, for today's topics, we're going to not leave these behind. We're going to use them. There's the function again. But we're going to talk about the same thing as we did when we did quadrature. Remember adaptive Simpson, where we wanted to estimate the error. Guess what? You want to do the same thing now. This was actually a bad example, although eventually you could actually imagine here that you would want smaller steps in the beginning, and then as it settles down, you could take bigger steps. Same argument as when I said, suppose you want to do Simpson's method from here to there, and you have crazy things here, but small here. You wanted to have adaptive step sizes. We made a big deal about how you, in fact, the trick then was to divide h by 2 and be able to get the error out. And there are so many ways, but we want to do exactly the same thing here. Remember, this function did not do it. This function asked you how many steps to take. You have to tell. The h is immediately given by that, and this is what I would say equal step size, right? So you take your interval and you do equal step size no matter what all the way to the end. That's a nice for toy problems like we do, but in the real world, usually you need to change the h as you go. So the topic now is, in fact, the section is called error control and step size because they come together. You need to be able to look at the error, and if it's too large, you should control the step size. So let's start by the first part. How do we estimate the error? Let's go back and look a little bit at ODs here in these methods. What do we have? So topic is error control. And just like we did back in the quadrature, you already have an error formula for Simpson, right? Oh, sorry, for Euler's method. But remember, it involves this big M, the bound on the second derivative. There's a Lipschitz constant. It's not practical, OK? So just like we had a strict error bound for the integrals, we still appreciated this little approximation we did with Simpson with a factor of 15, remember? So we're going to do a similar thing. We need some easy thing to estimate. And what are we estimating? Well, the setting is this, as always. We're going from ti to ti plus 1 with, for example, Euler's method. Let's say that you start at, I don't care where you start. I mean, the history is one thing, but let's say you start at yi, and this is the true solution yi plus 1, which you remember is a shorthand for y at ti plus 1. That's the true solution. But your method does not know how to do that, so it's going to produce a wi plus 1 that is wrong. OK? And if you remember the definition of tau local truncation error, it's really this error, although there was a factor of h. So you could say that this is h times tau. And the tau is always different, so we put a number on tau as well. Okay? But tau local truncate, it's really the error you make in one step. Okay? And you know, if this curve here was a straight line, I could take really big steps and not make any error at all with Euler. If it has a lot of curvature, the big M, the capital M in the expression, then it's kind of bad, and I should probably shrink h, right? So in a way, you want to estimate this error and tell me what it is. How could you possibly do that? So it's going to be the ugliest, simplest trick in the world, but just thinking about it, if you tell me the second derivative, Taylor would tell me a bound on that. We had that bound when we derived the error formula. But I don't want you to be able to tell me a bound on the second derivative. I want to just automatically do this. And there are a bunch of ways to do it. The method they propose here, which is really widely used, is to waste some computations and compute a more accurate step. You remember when I did this with Euler for my test problems, and then I did the Taylor method of order 2. Euler was really far away, and Taylor method looked like it was right on top here, right? It was so much closer. And the truth is that to first approximation, if you just take one step and want to estimate this tau, clearly the error is the true solution minus what you computed, but we don't know the true solution. But to first approximation, you can say it's a better method minus your method. So you see that it sounds like a bad thing, but if you take one step with a better method and one step with Euler, subtracting them should give you an estimate of this jump. That's the simple method they do. It's unclear why this ended up being the winning methods, but the simplicity is certainly one of them. here's in words what we do. Estimate tau by taking the step, and by the step is, of course, from ti to ti plus 1, taking the step with two methods of different order. Okay, and it's all in the slide up there, and I'll show you there, but I'll make it much simpler here for you guys. So you have your method. We know that it has an error that we call tau. Okay? So this is, for example, Euler's method. It will take a step, and it will produce wi plus 1 that is wrong, and it's wrong by what we call the tau. Okay? And maybe I messed up the sign here, but the sign of tau doesn't matter. But then you have another method, let's call it twiddle, that also works, but it's better. It has a different tau, tau twiddle. Okay? And by better, I mean fundamentally better, or higher order. Where tau I plus 1 is order, let's say, h to the n, but the tau twiddle I plus 1 is order h to the n plus 1. All right, so just think in terms of this being Euler and this being the second order Taylor, or the midpoint method, whatever method. Midpoint is better to think of. It's one step more accurate. And we want to estimate this. This is the error that you want to control, or maybe times h, doesn't matter. Now, since this is super tiny, it's a higher order, it should be much smaller. So to first approximation, you can set it to 0. And then clearly you can estimate this tau by just subtracting these equations. And in fact, you'll end up getting basically what I said. To first approximation, this other wi tilde, let me put it here, if I don't mess it up too much. Here is wi plus 1 twiddle. It's also wrong. Everything is wrong, unless we're lucky. But it's much more accurate. All right? So to first approximation, this jump is approximated by just the difference between these. Ends up being quite simple. But subtracting these equations, you can get tau out of it. And it's going to be exactly equal to tau twiddle plus 1 over h of this w twiddle I plus 1 minus wi plus 1. But then you say that this tau twiddle was one higher order than you expect. So why not just say this is approximately equal to 1 over h of w twiddle. And this is so easy to remember because it's really what I said. It's just the difference between the two steps. And then divided by h because that's the definition of, that's in the definition of tau. Really easy to estimate this. Which means that every time you take an Euler step, you take a more accurate step as well. And subtracting them tells you what the error is. There are many questions you should have. One is, that's kind of a waste, and that's true. But they figure out how to reuse this case a little bit, so that's not so bad. But it sounds certainly quite not bad. A more common question is, why would you even keep this method? So every time you take a step, you're doing the Euler, and you're doing this much better method. Then you're keeping the Euler. That sounds completely insane, because you have a better result here. And that is insane. And some people just violate that. But that's the way we can control this error. By running a better method alongside, we can monitor how bad the bad method is. But people do all types of variations on this. But anyway, this is the step of estimating tau. And as you see, it's almost as easy as this factor of 15 with Simpson. Remember, the rule back then was not that we ran two different methods. You could have done that. But you ran two different h's. We did Simpson, and then we divided h by 2. And the difference divided by 15 was an estimate of the error in the accurate one. Very similar. You just run things twice, and you look at the difference. In this case, this is what comes out of it. Now, what do you want to do with this number? This is error estimation. We estimated the error. So here's the error. What should you do with it? So one thing you could do is that you could take my RK4 function and output a vector of taus that you have estimated. That could be a pretty nice functionality. That you do exactly what I did here, And then alongside, you would get one more vector out called tau, and it would tell you what the error is. And it's actually quite useful. But we want to do more. We want to control the step size. That's the big goal. Because you take a step, and you get a tau, then you can do a bunch of things. In fact, what the user wants here is not to tell you how many steps to take. Imagine that you're a physicist, and you want to solve an ODE like I just did here. Do I really want to tell this big N? If you imagine how I probably want to operate, I mean, of course I have to tell the computer what my function is, and where I'm going, and what my starting condition is. But this N is a numerical thing. I don't want to have to do with that. Maybe I don't even understand it. I don't know my equation. I don't know what I want. What would I like to tell the computer instead? Nothing would be good, but I need to tell it something. Yeah, you want to tell the error. And it's a little iffy because it's just approximate, but that's what the user thinks of. We all know that if you want really accurate, you have to take more steps and smaller h. But you don't want to talk about the number of steps. You want to talk about the error. So typically, I want to say 10 to the minus 3. Or maybe I really want a good answer, then 10 to the minus 6. That's what I want to tell, instead of big N. How do you do that? Well, assuming that this corresponds to the error, that is a big if, by the way. Remember your Euler formula from chapter 5.2. That was an error bound. This is just a local one-step bound, but that's all we can control. And that's a whole separate discussion. But let's say we accept that this is an estimate of the error. How can you control it? So here's kind of what we're going to do. You're going to choose an h, whatever, small or large enough. You're going to take a step. You're going to estimate tau. What if it's larger than your epsilon? Can I keep the step? I already took the step. I estimated the error to be 10 to the minus 2. But you want it to be 10 to the minus 3. I cannot keep the step. That step is bad. It's too large error. You reject. You throw away the step. And what should the new step do instead? Make h smaller, right? So you tweak h. You basically reduce h. And again, we're going to use the math to figure out exactly how to reduce it. But then maybe you take a step, and it's 10 to the minus 3, and you're happy. And then you can take another step. OK, what if I take a step, and it's 10 to the minus 4? Then you might want to increase it. Not too much, but you know. And you could say, no, you don't have to do that. Well, it's a question of efficiency. Maybe the function really plateaus out and does nothing. Then you want to increase it a lot. And you can do that. Yeah?
So this is basically adaptive quadrature?
Yeah. Well, we don't use the word quadrature. We use ODE solvers or integrators, right? But it's really very similar to what we talked about for the composite Simpson. When you have an error estimate, you can control the step size. And the question is just how you do it. But yeah, that's all I'm trying to say. Let me just tell you that little part, and I'll show you a computer code for doing this. Here's just a few words about if this is something that you don't like, or like 10 to the minus 2, and you want it to be 10 to the minus 3, how should I change h? Should I divide it by 10? OK, so say that you want tau to be less than or equal to epsilon. Let's say 10 to the minus 3 for now. Estimated tau I plus 1 is 10 to the minus 2. You want to change the step size, h, new step size. And if it was h before, it should be something smaller now. Let's call it qh. How much smaller? 10 times smaller? Yeah, that's the answer. That depends on the method, right? But yeah, if it was Euler, like I said before, then it would actually be 10 times more, because that's a linearly accurate method. But if it's one of those fancy methods, the whole idea of high order methods is that you remember, you divide h by 10, and the error gets to power of 4 more accurate, right? So if this is the amazing RK4 method that we just did, it would be a complete waste to divide this by 10. That would make it 10,000 times more accurate and you would completely overshoot your target. So you want to do something involving like a fourth root of the ratio here, right? So let's solve for that. I'm just saying it depends on the method. In fact, it depends on this tau here. If this tau is ordo h to the 1, like Euler, then you know the error scales approximately linearly with h. If you want 10 times more accurate, you divide h by 10. If this is h squared, you probably want to divide by the square root of 10. And so let's figure it out. It's actually very easy. You just set this up, and you get an expression out of it. All right, so the goal is find new step size, which is a multiple of the previous h, such that the new tau will stay, well, less than epsilon. Okay? So this is what we do. You had a tau, and I'm going to put a parameter on tau because the tau, I'm reusing the notation tau I plus 1. It depends on h, right? So since I'm changing h, we need to indicate that. So you told me that you got something, and we know it scales with h to the n approximately. That's the same thing as saying that it's order hn, but it's a little bit less precise. That means that when you multiply h by q, it ends up being k times q to the n times h to the n, right? But that's approximately equal to q to the n tau I plus 1 of h. So in words, you're taking a step with step size h. You're estimating the error. Now, the factor you multiply it by will be taken to the power of n, approximately, for your new step size. All right? So this we approximate now using our little method here. So it's q to the n over h times this difference of the two methods. So this is just repeating what we did over here, just plugging in that. And I'm doing absolute values because I don't know if tilde is bigger or smaller. I don't care. I'm just estimating the error. All right? And you want this to be less than or equal to epsilon. How do you do that? Well, you set it equal to epsilon. You know this. You just took those two steps. You know an approximation for tau divided by h. It's going to be a nth root of something here, right? So this gives epsilon, sorry, q. This q is what I want to compute. So q is equal to, well, less than or equal to, epsilon h over this jump minus wi plus 1 taken to nth root there. It's kind of easy. It's really as easy as you would probably figure out yourself. You know how it scales, and you want to go from there to there. You can figure out what to do with it. Do you notice that this includes the case when this is too small? So if you want 10 to the minus 3 and you're getting 10 to the minus 4, this will work fine. And the q will, of course, be greater than 1. It will tell you how to increase the step size. Is it a good idea to set it exactly to this? You know, there are approximate signs all over the place, right? So you want some. There's going to be a little bit. All this is pretty rigorous and nice. I mean, it's approximate because we're ignoring higher order terms. But in an actual code, you want some magic numbers, saying that hey, let's not go. I mean, you need some margins here, because theoretically, what we did, this would put you exactly on epsilon, right? And that's a little too scary, because if you go a little bit above, you have to retake the step, and it's a waste. So there are some things like that going on. Let's see if the slides have some recommendations on that. So here's what we did. You run a Runge Kutta method with W tilde. Here we're talking about one specific method, which they focus on in the book. And you're going to run it, and you can use the code we have for it, but it's called the Runge Kutta Feldberg. But you have a W tilde that is more accurate, in this case order 5. And then you have a less accurate, in this case order 4. But it's, of course, super accurate, so it doesn't really matter. And the steps control strategy is, of course, this, that if q is less than 1, okay, so every time you take a step, you compute this q. And if it's telling you that q should be less than 1, that's the same thing as telling you that your error was too large. you have to reduce the step size. It's very important to realize that then you have to reject the step. You cannot keep the step because then you can't. You have a user, right, who doesn't know numerical methods, and you wrote this code for them. And they're saying, I want the error to be 10 to the minus 3. I mean, you need to tell them all the disclaimers that this is all approximate. You're not guaranteeing anything. But it would be a shame if you knew that even according to all your approximations, you made an error that was greater than epsilon, like in this case, and you kept the step. You can't do that, right? So you got to reject the step if this is greater than that, which of course is the same thing as this expression saying that it wants q to be less than 1. If q is greater than 1, it wants you to increase the step size. Then you can accept the step. You took a too small step size, but it's fine. It's accurate. It's just too accurate. And then you change the step size. This is the method. Anyway, so here's how they did it in the book. You know how I tell you that sometimes I don't know if the book wants you to use existing codes or implement from scratch? Here I think it's a clear example where you got to use the code, because it's a little complicated. You can see the book. I just followed it completely and rewrote it in MATLAB. And I called it RKF, as in Runge, Kutta, Feldberg. And I'm going to show, it looks a little bit like a mess, but it's just because the method is complicated. So this is all in the book. And for your exercises in this section, you can use this function. What I want to talk a little bit about is this, what I do with this method. So there's some magic, but especially you see an expression here popping out that is exactly corresponding to this here. All right. So let's look here. I should probably have written a simpler code that really just did Euler and midpoint method just to make it clean. But let's go straight at the actual function here. As I said, you always need to tell it what the problem is, which is f, a, b, and alpha, right? How could you possibly solve the problem without knowing that? This, a common word for epsilon is tolerance. Tol is often used for that. That's the epsilon, what error you want. This code has two other, these are practical things I didn't mention. Turns out that, I don't know, sometimes you want to control the smallest possible h and the largest possible h. In an ideal world, you could set the smallest possible to 0 and the largest possible to infinity. But I could show you where that goes wrong. For example, if you're stepping, if you know your function is not doing anything and then it starts doing things, if you take big step sizes, you will miss it completely. So sometimes you need to tell it to, hey, step at least in minutes here or something, right? I mean, it's practical details. Let me show you how this, just a computer language construct. Why is it not a for loop any longer? I don't know. Remember these rules? At the for loop, you know what you're going to do. Last time, I knew I was going to make big n steps. Now I have no idea beforehand how many steps. That will come out as I go. So I need something more adaptive. Anyway, you're grabbing your current w and your current t. And if you look at all these expressions, it really looks like any old Runge Kutta. This is the Euler slope. And I'm doing all these offsets. And there are crazy offsets that we're not going to analyze. But it really fits exactly the pattern from the midpoint or the RK4. And the end result is 6Ks. And the way they write it in the book is that they immediately write out an expression for this here. So as I described it, you should compute one accurate and one less accurate and divide by h. Well, guess what? They immediately do a combination of k's and divide by h, and they call it r. So this r is, not sure exactly why it's called r, but it's an estimate of the time. So we have it here, and we can get the actual function out. We're going to do that soon. But here comes the logic. If r is less than tol, which was epsilon, what should we do? We should keep the step, right? Accept the step. And the way we do that is that we move up t by h. We have an indicator telling how many steps we've taken I. We put this t in the list of all t. Variable names are weird sometimes, but t is just the current t, and all t is, it's what it sounds like. What is this? Here's the actual computation. This is just like Runge Kutta. You remember that we want to add up, and these are also these magic numbers. So if this was the midpoint method, it would just be k2. Now it's all this stuff. And finally, we put that solution. So we took a step, and we kept it. All right? What is this? This is, and again, I apologize that all the notation is different. This is q. So I don't know if I changed it or I don't know. But this is q, basically. And let me tell you where it comes from. Tolerance was epsilon. The r was this entire w tilde minus w divided by h, named the tau. So going back already here, that this whole expression, tau, was the estimated r, right? So really just taking what you want it to be, epsilon, dividing by that, and then the nth root of that to the power of 1/4. Because the less accurate method was fourth order accurate. What is this? That's my little margin that I said, let's not be right on the boundary there. And I think this is chosen so it's a factor of 2 in the error. Yeah, they just said, oh, let's have a factor of 2 of margin in the error, which corresponds to a factor of 0.84 in the step size. This is magic that I don't want you to care about. Turns out, if it says, hey, you're super accurate, why don't you just divide your step size by 100? It's a good idea to go be a little cautious and just divide it by 10. So if it's telling you that you want a Q here is super small, just do a factor of 10 at a time. And then, of course, next step, it can tell you another factor of 10. That's OK. But don't change it too much. Same time, if it say, look, oh, this is the other way around. You're super accurate. You can increase it by a lot. Well, don't increase it too much. But basically, what you're doing is this. Namely, you take your h and you replace it by delta h or qh. You're changing the step size. And also some other logic h. This is not important. All right? I know it's a little maybe confusing, but it's not that weird. Let's use it. Let's run it on what we had here. So basically, you do exactly what we did. F010 alpha. Instead of 100 steps, I'm going to tell it an accuracy. And let's tell it 10 to the minus 3. And then I have to tell smallest h and largest h. That's the way it is. Let's see if it freaks out if I do that. That's a little risky, I think. RK F. OK, it didn't really, what didn't it like? Let me see what it didn't like here. I don't think it was this, but well, alpha tau. All right, this is some debugging. Alpha is 2 numbers. F is a vector. And it's crashing there. OK, then I'll teach you some debugging. You do the db stop if error. And then you can look why this is freaking out. Tol is a number. R is a vector. Yeah, I know. Actually, the truth is that this function is really just written for scalar cases. It's this R, everything is expected to be a scalar. It's also a little unlogical. It's very easy to change, but OK, your homeworks are the same. So let's do a different model problem. Let's do my favorite. Let's do minus y, so it decays out. OK? And now we start at alpha equals 1. Yeah, now you can update it easily to handle the case from before. Let's go back here. I'm greedy. I want this to happen. It didn't work. It decreased it too much. So let's do 10 to the minus 8, 10 to the minus 1. OK, that works. So when it runs, you get a list of times and a list of numbers, W. And we're going to plot them, of course, but let's just look at them. There are the times, and there are the W's. Let's plot them. And you really want these indicators here of the step to see what it did. This doesn't look too impressive. And that's because I set an h max to 0.1. I don't want that. Let's recompute it with 10 there. OK, this is better. It's going all the way from here. Remember, the true solution is 10 e to the minus x. And you can see that it's doing some good job in increasing the size here, maybe not too much. But what if we make it more accurate? I want 10 to the minus 6 now. Well, it's throwing in more and more points. And it's a little difficult to see here, but you can see that at the end, it's trying to increase the step size. That's something it can do, because I'm telling it can go really high up there. This example is not a perfect case of where you need adaptive step sizes. As I mentioned, a perfect example would be something that does very little and then suddenly does a lot of crazy things, right? but some things are not. This is a pretty uniform function, but you can still see that it's doing this sharp decay here, and then it's increasing the step sizes. If you want to look at the step size, there's a function in MATLAB called diff, which looks at the difference between pairwise. So you plot this, typically, we could plot it if you want to, but typically you want a log scale. You can see that it's starting at a step size of 0.1. You can see many things. You can see it's taking about 30 steps. It's starting at the step size of 0.1. If it kept that step size, it would have to take 100 steps. But it says, hey, we can increase it quite a bit. And then at the very end, there was just a little correction. That's not so important. All right? More extreme case. How do we make it more extreme? Well, maybe if we go further. Here it figures out, so this is an interesting case. In this case, I'm going all the way to 100. And it does increase. And you might be surprised that it doesn't increase the step size too huge, because the solution is really 0 after time 10, right, or 20. But there's something called stability issues. That means that it cannot increase it too much. And it's actually quite amazing that it figures out that the step size it can do without causing trouble is about 3. Automatically it figured that out. So this is really pretty good stuff. But it also figured out it had to start really small in the beginning. Let's even more strict tolerance. I don't know how far we can push this, but 10 to the minus 8. It's, of course, putting even. Now you want the log scale here for sure. And abs values here. So let's look at the steps it's taking. It starts at 4 times 10 to the minus 2. Because why? Because I told it to be much more accurate in the beginning. And then it still increases it to 3. So this is the power of it increases it by 2 magnitudes. Again, imagine if you wanted this, if you want to do the same error with RK4, you would have to keep that small step size for the entire cycle. I'm just saying it's a bad idea to keep the same step size. It might not be needed. You might want to do something like this. Anyway, you can use this function for there is 1 or 2 exercises in this chapter. And I'm pretty sure they want you to use this function. But you have to also independently trying to figure out that you know what's going on. Except for all this magic going on here, I think the main steps was what we went through here on the blackboard. It's actually quite straightforward. A simple, very simple strategy for estimating the error. And given the estimate of the error, you can compute a Q that keeps the error around epsilon. So it's the big plan here is quite simple. And by the way, when I teach this in the grad course, I show them what's available out there. There are packages for this. In MATLAB, there is a big thing called ODE suite, which is a set of functions doing these things. And they are all based on these methods. They never let you say how many steps to take. There is something called OD45, which all electrical engineers are going to use at some point in some class. And it's just based on exactly this method, Runge, Kutta, Felberg. And you tell them errors, and there are some differences, but it's basically what they are doing. So this is really close to reality. The only thing you might want to ask yourself, why do we need to learn it? And that's because, you might ask that question about a lot of things. Why do you need to learn this when there are perfectly good software doing it? That's because you're considered the people that might actually end up improving and developing these things. But yeah, a lot of these, it's like I said with the IEEE standard. A lot of people just fire up Excel and compute, 5 divided by 3, and they think it's exact. But as we told you, it's not, because it's base 2 and there's epsilon and stuff, right? Who needs to know and who doesn't need to know? Most people do not need to know about floating point standards. But in numerical analysis, we know it, right? So same with this method. It's kind of very mature. And you can use software as, if I want to just solve an OD, I'm not writing my own software. I'm using the packages. But you got to know how they work sometimes. All right? A lot of stuff. Are you guys confused? Any questions? Yeah.
So do we use W for the W filter?
So this is so iffy that it's unbelievable. The way I describe it, it's super clear. And this is what the book does, and you should do it. We keep the inaccurate one, W. Otherwise, our tau is not estimated correctly. In practice, real codes here, they of course say, hey, I have done all this work, and I could do what we just said. But look, at every step, I have something that I know is more accurate. Let's keep that. So people do that a lot, but we don't. Because then the tau is just wrong. And in fact, it's probably too large. But what's the damage of taking the more accurate one? So this is a big issue in this field. Which one should you keep? The theory doesn't allow you to really keep the old one and say that it's a tau is an estimate of the one you kept. So we keep the inaccurate one. But I agree that it's weird. Yeah, so roughly you have this, right? Order h to the n and order h to the n plus 1. So you could do that. You could take your estimate of tau, and you could basically multiply by h. But there's also a constant in these, but you can estimate those. So when we analyze these methods, you can actually figure out, when I say order hn, I really mean k times h to the n, right? So I can estimate that k. And there's another k here. So if you want to, yeah, you can definitely estimate that tau. The problem is that then the error you made when you subtracted and did this here is suddenly now fundamentally large. Because then you can't really. So what you're saying is that you're trying, look, this is a true solution. This was the bad method. This was the good method. I said to first order, this error is approximated by the difference here. Now you're trying to estimate the difference up here. And even if you can get the scale right, that is not justified any longer. Or in other words, this guy here doesn't tell you anything about the error in the good method. So, but yeah. What people do is they don't do that. People do what we said, and they just keep the good one without comments. That's a little ugly. Yeah?
So looking at what back into this, so I initially thought that oUSJ4 means that we're using the fourth order of and then we're using the fifth, and then the 5 part is how we're controlling
yeah.
what we're using to control the error.
Which is, I think, we could look exactly what that method is doing, but this method does exactly that. It's a fourth order that you keep, and the fifth order to control the error. And I think our oUSJ45 is exactly that. There's a lot of documentation here. Let's look at 45. At the end, so here they tell you how to use them. Here they have these cool examples. Oh, this is good, cool. Here's one of those extremes examples I talked about where you really need step size control. They make up functions that are actually quite realistic, like explosions or things happening suddenly, right? So you see this blue curve here. Very little is going on, and then just the sharpest increase in the world. I think the step size here is probably changing by 5 or 6 magnitudes. And if you wanted to do this without adaptive control, you would have to choose that small size for everything, and it would take probably a million times longer to simulate. Anyway, just to see the methods, at the end here they talk about the methods. Oh, they're doing the Dorman print. It's very similar. It's not exactly the Runge Kutta Feldberg. It's a slight variation. But it's the whole strategy is kind of similar. You know, by the way, MATLAB is kind of cool that you can just look at these functions. So if there is a fancy function in MATLAB that is written in MATLAB code, some are not, then you can just do this, and you have their code. I want to warn you that they are very long for various reasons. One is documentation. This is all comments. Another is user error control, right? Check inputs, not enough input. It's just more annoying. When we do this in a class, we just assume a few things. And you notice, like for example, the mistake I just made of sending in a vector to my RKF. It should, of course, have said, sorry, I am only implemented for scalar equations. But it didn't. It just freaked out. So they do a better job here. But it's kind of nice. You can actually go in here. Here, for example, you have the method. Here are all these numbers. You could go in and change it if you want to. Here you have something very similar to what we did before. There's a power of something, but I don't know exactly what they're doing. So that's kind of nice. Not too much magic. All right. Are you ready for a new class of methods? And you might want to ask yourself why we need more methods. Haven't we completely solved it? And the truth is, yeah, Runge Kuttas are really quite dominating. These are working fine, and it's a good idea to start with them like this, because they are very important, and they can solve most problems. There is a huge class of methods that people use as well, multi-step. And they're so common that I guess they thought that we better talk about them a little bit. And it's interesting what they do about them. It's suppose you're standing at ti, and you want to get to ti plus 1. All the methods we talked about can take you from there to there. Okay? Euler, obviously, it just stands here, it takes a slope, and it takes a step, right? Runge, Kutta, it seemed like I did a lot of weird things, all these Ks. But if you think about it, I really started here and went to there. These are so-called one-step methods. And it's very natural to do. But if you think about it, I've taken a lot of steps. So I have a ti minus 1 and a ti minus 2, right? And I'm presumably, except for when I start, I have a bunch of old numbers. And multi-step methods are going to look at those and see if you can create a better method. It's actually very natural in many ways. Let's look at probably the most, I mean, clearly it's more information. So why wouldn't we be able to do something better? Let's look at just Euler to begin with. What did Euler do? It's standing here, and it's saying there is a slope, and that's called f, right? And we're going to assume that it's constant, and we're going to take a step of that constant, like that. Okay? Another way to say that is that if you don't mind me drawing f down here, so this is y of t. These are, of course, my w's. But there's an f as well. Now I'm drawing it as negative. Maybe that wasn't my purpose. But there's an f. F of t comma y of t, right? These are the slopes. And it doesn't correspond to my figure because these are negative, but it looks like it's going up. But just conceptually. So what did Euler do? It was standing at wi. It took this slope, f, and it said it's going to be constant for this time step, which is the same thing as saying I'm going in a straight line up to there. Okay? It is what it is. It worked, and it's not very accurate. If I have these old guys here, what could I do? If you look at what we had here, I don't have this. This is the future. If I just, Euler didn't really know much more, right? It really just knew that f. But if I have this guy here, what's a better approximation? Clearly, the reason Euler is bad is that the slope isn't constant over the time step. It's changing, right? But it doesn't know how it's changed. So what we did was that we took a step, and then we said, look, now we better stop and compute a new slope. If I have this value here, what is a natural thing to do instead? Yeah, this is the most popular. This is a huge class of method called Adams methods, or Adams-Bashforth method. Saying, look, so previously I just had this, and all I could say is just that it's equal to that slope. But if I have these two guys, why don't I put a straight line? And this here is an f that I can use. The way I draw it, things are varying too much, so it doesn't look that much better. That will, of course, mean that this curve here now becomes basically a parabola, because I'm going to integrate the straight line. But it's kind of nice. What am I doing? I'm using old values. It's going to involve wi minus 1. That's OK. I will have it, except when I start, which is a separate problem. How can you generalize even more? Pretty obvious, right? You said the word polynomial. Just bring up the polynomial. There's a whole class of methods. Why don't you put a parabola through these three? Integrate that parabola from there to there, and you get a new wi plus 1. I mean, we're not going to do this in practice. This will generate methods. And they're very short and easy when we're done. But the first main step is, let's see what happens if we're allowed to use these old values. And there are whole classes of methods that can do it. Let me derive one of these. Just some notation. First of all, let's define f. You know how I like yi. We've done this one before. Yi is equal to y of ti, right? But I'm also going to do f of ti, yi, fi. Okay? And now we do what we said. Let p of t interpolate some of these old f's, right? So here's a fi, and this is fi minus 1, and this is fi minus 2, right? And there will, of course, be an fi plus 1 in the future, but we don't know it yet. So it's going to interpolate fi minus 1, And you can imagine going all the way down to, let's see, r plus 1. For a total of r points, right? We get a whole class of methods. So let's look at r equals 1. What method should that give us? I'm interpolating only through fi. As we said, that should be Euler. So I'm doing that just as a warm-up to say that then clearly my polynomial p of t will be the constant function, well, fi. That's a simple polynomial, right? Now you want to integrate this, and that's, of course, all based on calculus, fundamental theorem of calculus. Tells you that if you tell me the slope, I can tell you the function by integrating, right? So in our language, it means that I plus 1 is really equal to yi plus the integral of the slope from ti to ti plus 1. And that slope is really f, t comma y of t. Right? This should not be a surprise to anyone. This is fundamental theorem of calculus coming out of our problem with just substituting for the y's. This is exact. Am I going to get the exact result? No, because I don't know this. This is going to be approximated by p of t. That's the whole game. So again, in the simplest case, all you do is that you're really lazy and you just say, let's approximate it by a constant equal to f of I. And of course, integrating then is trivial, and you get a method. So now I replace it by w's, because now it's my method. And integrating a constant from ti to ti plus 1 is the same thing as saying h times that constant. And this is, of course, nothing but Euler. Right? But it's a warm-up to see where we're going. So now let's bring up r to 2. All right, Lagrange form of polynomials. What is this? So I have 2 points, right? I have fi and I have fi minus 1 at time ti and time ti minus 1. I want to draw a straight line between them. You all know how to do it. The equation of the straight line you did already in high school. But of course, we love our Lagrange form, so I can just write it straight out. The function value at one point, fi, times, and remember the t minus the other one, over t myself minus the other one. Right? This was the L0, or that L that was equal to 1 at point I and 0 at all the other ones, multiplied by function value. And then you add in the other one. I think that is the straight line that I messed up here, but drew it here, basically. All right, we'll finish this up easily. All right, so what is the method? Now you integrate that. Integrate p of t, and you get the method, which says that I plus 1. So basically the y's turn into w's because I'm approximating, right? This is true for the true solution, but I approximate, and that gives me a method. And that's going to be what? You just integrate this. It's, let's see, fi t minus ti minus 1 square halves times ti minus ti minus 1. I just integrated a linear function. I got a square divided by 2. Then plus fi minus 1, and I do the same thing again. Slightly different numbers of ti minus 1 minus ti. And I'm plugging in ti and ti plus 1. Okay? It's really just integrating a linear, a straight line. Just reminding you that ti minus 1 is h. Ti minus 1 minus ti is minus h. I'm going to plug in ti plus 1. This becomes 2h. So sorting all this out, you're getting wi plus fi times, when you're plugging in that, you get 2h squared. You get 4h divided by 2h. 4h squared, sorry. Then you're doing this guy, plugging in that, and you get, well, let's do the ti first. Then you're getting minus h squared over 2h. Then you're getting the next one, I minus 1. Plugging in ti plus 1, you get an h squared here. H squared divided by 2h. And that's it. Because when you plug in ti into this guy, it's equal to 0. Now you're just going to clean this up a little bit. And you get the method. And let me just write it, and then we justify it. Plus, I think it's going to be 3 halves h multiplying this guy. And it's minus h half multiplying that guy. Let's see if that's correct. Yeah, this is minus because this is minus h instead. So there is your minus a half of h multiplying fi minus 1. Here you're getting 2 minus a half, which is 3 halves h multiplying that. This is the method. It's called the Adams-Bashforth method of order 2. And it's very simple, isn't it? But you need to remember your old numbers. There are a lot of issues when you actually start implementing this. After you've been running for a while, clearly you have a bunch of old apps, and this is going to work fine. How do you get started? How can you take a step? When you start at 0, you don't know this guy, right? It's a big problem with these methods. But these methods can be quite good, so people are willing to do stuff to overcome, and it's kind of ugly how they fix it. But as soon as you get started, these f's, remember, are just f's you compute at every step. You do a very simple calculation, similar to Euler. Remember, Euler is really just wi plus h times fi. The only difference here is 3h half fi, and then minus a little bit of the older f. And you're getting, this turns out to be just like the Taylor second. This is a second order accurate method. So it's quite impressive. But we'll do more about it next week. Thank you. I have office hours now, if you have questions.